Good morning, everyone, or good afternoon if you're in Cairo. Thanks very much for coming and participating in this session. The focus today will be on measurement, instrumentation, control, and analysis, a system called MICA. And our presenters will be Professor Ian Hunter and Dr. Lynette Jones, who together run the bioinstrumentation lab at MIT. Professor Hunter is the Hatsopoulos Professor of Thermodynamics at MIT. He is a prolific inventor and fellow of the American Academy of Inventors. He has done work on instrumentation, system identification, actuation, and applications, especially in medicine. And Dr. Lynette Jones is a senior research scientist at MIT, and they have both earned their degrees, their bachelor's degree and master's degree at the University of Auckland. Professor Hunter earned his PhD at the University of Auckland, and Lynette Jones earned her PhD at McGill University. And they built a remarkable lab at MIT, and in that lab have invested tremendously in this rich system of sensors and interfaces and displays, and this system is quite flexible and modular. And so we're excited to show it to you because we think it shows real promise for universities seeking to navigate through this disruption that we're all experiencing. So without further delay, I want to hand over the control of the meeting for the next 15 minutes to Ian Hunter and Lynette Jones. Thank you so much.
Our pleasure to join you today and give an overview of the MICA system that we have been working on for a number of years in the lab. Okay, just a minute. So the impetus for the development of MICA was really the need to rethink our approach to STEM education. Existing disciplines have become entrenched and lack the flexibility to adapt to new changes in instruction and in technology. We know that the chalk and talk style is inefficient and lacks hands-on experience for the students. And clearly one approach does not fit the needs of a diverse range of students who vary in their learning styles, their aptitude and skill sets. And so we think of MICA as very much a tailored education system, a bespoke one, if you like, one that can work with the particular capacities of students and adapt the learning methods and the materials presented to those particular capacities. So by analogy to how people learn to play a violin, which is not just to learn to read music and look at how violins are made, but actually to interact with the violin itself, we consider MICA with its experimental workstations to be the means by which students can perform experiments, analyze data, they undertake parameter estimation, they fit mathematical models and learn theory. And all this is accomplished under the guidance of a virtual tutor that called a MICA avatar that is under development at the present time. So we can think of courses that are often taught in engineering as those that involve building systems, those that involve using systems, and those that involve the combination of the two. In the context of the MIT MICA undergraduate education, in the course that Ian Hunter teaches, the Measurement and Instrumentation undergraduate course, it's very much a use-it course. In other words, students use sensors, actuators to make measurements, they analyze those data, they fit models to the data, and that may involve systems developed by Pasco, Vernier, and other companies that make educational materials. When you talk about building systems, from those of us in early childhood who use Meccano sets and Legos and so on, we think we need the building blocks that enable us to put together these systems and then incorporate the sensors and the actuators to get them to perform the particular experiments that were of interest to us in order to understand some fundamental phenomena. MICA has evolved over the years, both in terms of the hardware and software systems that are used, In particular, as the dynamic range and bandwidth of various sensors and generators has steadily improved, we have been able to incorporate the benefits offered by those changes into the systems that we have developed. The size and the price has dramatically increased, often with those developments. So we have used these systems. This is not only a research project in a number of courses at MIT, from the undergraduate instrumentation and measurement laboratory class, which has 140 students a year, to a couple of years ago, we used a particular sensor system in the undergraduate first year physics class, which involved using it with 585 students. And then more recently in the advanced instrumentation and measurement class, we have used a number of the MICA workstations, in particular over the past semester, in which we were doing online learning that Ian will describe in a few minutes. So this is the kit that was provided to all the first year physics students taking 801. They were enabled to use this in any context they wanted to make measurements of the motion of particular systems that were of interest to them. They learned the workings of the MEMS accelerometers in their lab classes, and then were free to take these systems out to make measurements in the real world. So we think of MICA as being a hierarchical system where we go from the lab course workstations, the benchtop systems that students can interact with that may be focused around a particular STEM theme, the environment or energy. Then we have modules that encompass the capacity to signal measurements. We have elements, and then we have components. And so these are examples of various mechanical components that we would have in a MICA workstation, the motors and actuators that we may need depending on the particular focus of that workstation, the hydraulic components, optical components, again, depending on the particular system that we've developed, and then the various electronic systems that we've used. We use both Tinkerforge and custom-built modules that enable us to control motors, to acquire thermal images, to make measurements of sound pressure, atmospheric pressure, accelerometers, and so on. Then in the modules that we have, which are all Wi-Fi, we have the capacity to make measurements of particular aspects shown here, UV light, ambient light, humidity, etc. And these then become the crucial elements in putting together the MICA workstation. The structural components are Mitsumi elements that we can put together using brackets to give, again, a footprint that is standard. A maximum size then enables us to put these together in a way that they can be shipped and sent to particular places if we need to provide them to other researchers who are interested in using them. I'll switch over to Ian.
Right. Okay, so this is an example of a MICA workstation. This is actually a hydrogen fuel cell, a reversible fuel cell. And this allows students to look at water being electrolytically decomposed into hydrogen and oxygen and the ratios of those two gases. And then in the reverse case, they're able to see that those two gases can be combined to produce liquid water, and the energy released is measured. And because the power that you can extract is a function of the load, you can see that in blue there we have a large variable, it's a potentiometer, but it's actually set up as a variable resistor. And so the students are able to change the load resistance as seen by the fuel cell, and they can vary that to optimize the power being extracted from the fuel cell. And so in this particular case, the students would see a real-time measurement of the current, voltage, and actually the power. And so they can manipulate it to see how, by changing the load, you can maximize the amount of energy per unit time that you're extracting from the fuel cell. A number of the other MICA setups, including, for example, the solar panel workstation, it's the same issue. It comes as a surprise to students with a solar panel, for example, that there's an optimum load that you can, load resistance that you combine with the solar panel in order to haul energy out of it at a maximum rate. Now, this illustrates an important element of MICA, because in this particular case, a student is manually adjusting the load resistance. What if that apparatus was not directly in front of the student? How would they then manually vary the load resistance to determine the optimum resistance for extracting peak power out of the fuel cell? So you'll notice that we have a small NEMA 11 stepping motor that's actually can be off, in which case the student can manually adjust the resistance, or if the step motor is on and controlled from the computer, it means that a student can now remotely adjust that resistance. And that's a theme throughout MICA, that whenever we have a variable that can be manually adjusted or something that can be manually manipulated, we try and have it also so that that same variable can be computer controlled. So that allows us to either run the MICA workstations directly in front of a single student, or under remote conditions, such as we're going through now with COVID-19, it allows these workstations actually to be used remotely, and yet, students may not have the same feel that you would get when you're actually, adjusting a beautiful 10-turn wire-wound precision power potentiometer. But nevertheless, they can adjust that variable remotely. So bear in mind that that's a theme for all of the MICA workstations, that you either use them preferably by having it directly in front of the student, or you have remote control over that workstation. Now, there's a number of elements that I'd like to point out here. Incidentally, we've created about 50 workstations so far, and we're working on another 50 and have a further 100 that we want to build. So in this particular case here, we actually we use the digital analog discovery 2, which has got a beautiful 14-bit differential 100 megasample analog to digital converter. And we're able to use that, for example, to measure the electrical impedance spectra of the fuel cell in operation. This particular setup also can be either wired and controlled remotely, or it can actually operate under Wi-Fi, within a Wi-Fi network. Many of the measurements we made are in fact done to 24-bit precision. Now this here shows that particular workstation being built in a CAD environment. So for those courses where you want the students to actually build the workstation that they're about to use to perform experiments, we can provide you either with a video like you're seeing now of it being built, or even better still, a CAD model where it'll, in the CAD system, show you the system being built. And that allows you then to start and stop it, which you can do in this video, but also if you want to zoom in or move around, doing this in a CAD environment rather than via video is way preferable. We've also been experimenting with the use of Google Glasses and other 3D displays to enhance, the three-dimensional visualization of these workstations. So this is an example on the left of the actual workstation that was built, and on your right is the CAD model of that workstation. And you can see in the CAD model, we've got even the wiring is present in the model. That's a rear view of the workstation. That's a front view of the workstation, and here's the rear view of that particular workstation. All of the workstations are driven normally just with two 21700 cells. So these are the cells that are coming off Elon Musk's battery manufacturing mega factory. And what's interesting about them is they're 50 kilojoules each. So with two of them, you've got 100 kilojoules. And so that, for some of the setups, is nice because students, if they know how much power is being consumed during an experiment, they can calculate how many joules you have left in the batteries. So it allows the students to start thinking about some of the system level issues around energy management. Here's just a close-up of part of that workstation. Now, over the years, we've changed the software environment that we've used together with this system. So many years ago, MIT produced, in fact, what at the time was a beautiful symbolic language called Maxima. And it was both symbolic and numeric, and it was written in Lisp. A little bit after that, I produced a computer language, Nexus, that was used internationally for a while. And if you look at Nexus, it looks almost identical to MATLAB, but preceded it by about 5 years. We did use Nexus early on in courses, and then we started using MATLAB. We then moved to MathCAD, and because of the very poor support for MathCAD, and I know Dan, I think, has used MathCAD as well, it was a pretty frustrating experience. So a little bit under a year ago, we converted over to Mathematica. And the reason for that is that the key language requirements that we wanted for students to have in the environment, that they would both control experiments as well as to run experiments, gather data, analyze, and fit models, was we wanted each measurement to have a value, a timestamp, and incidentally, one of the big differences between Mathematica and MATLAB, Mathematica allows you, for example, to do a Fourier analysis on unequispaced samples through time, whereas MATLAB is largely, most of their algorithms are based on having uniform sampling rates. We wanted an environment where you didn't necessarily have to have equispaced measurements through time. We also wanted to have an environment where every sample could have a unit associated with it, preferably a metric unit. MICA is completely metric, by the way. And we wanted each value to have a plus minus uncertainty associated with it. And we wanted those uncertainties to propagate through all calculations. And again, Mathematica is pretty unique in its ability to propagate uncertainty both through numeric as well as through symbolic computations. Of course, the other requirement for the environment was we wanted to be able to do both symbolic calculations as well as numeric calculation. We also wanted an environment which would allow us to do lump parameter modeling, which of course MATLAB's very good at, but also continuum models such as finite element modeling. Now, one of the problems with Mathematica is that its timing, its timer, its internal timer is at best a millisecond. And if you happen to be running Mathematica on a Raspberry Pi, for example, it's 10 milliseconds. And that's simply not good enough for a lot of measurements. So using the fact that we've got quite a bit of experience in writing languages ourselves, and using the fact that Mathematica actually has got wonderful facilities for being able to extend the language, we actually have now extended the language so it has 100 nanosecond resolution time stamping. We also wanted support for imaging, video analysis, potentially molecular modeling. Of course, 3D visualization is very important, including the ability to bring CAD models into the environment. And then we wanted an environment where we could have e-tutors, avatars, that could replace physical humans where necessary. And that's under development. So this is just illustrating a couple of simple examples where you may want to compute a standard deviation either numerically on the left or symbolically on the right. I'll just skip over that. It's not necessary. This slide is really just to drive home the key modeling needs that we have. The need for lump parameter models, such as you'd have in typical control systems, Bode plots and transfer functions, and then for nonlinear Lamprometer dynamic modeling, Volterra series expansion, Volterra kernels. We also wanted to make sure that we had continuum modeling, finite element modeling, and Mathematica in particular has very recently got a relatively powerful finite element modeling capability, which interestingly, most finite element modeling packages are numeric. Think of computational fluid dynamics being entirely numeric. Mathematica, because of its symbolic capability, allows you to have combinations of continuum models that are both solved numerically and for a more limited set of cases symbolically and therefore exactly. You can do molecular modeling, DFT, as well as neural nets and deep learning. And we have been working hard on a method to combine lump parameter modeling with continuum modeling. And that goes under the name of Port Hamiltonian modeling. So there's now a nice mathematical framework where on one extreme you can have a lump parameter model, and on the other extreme you can have a continuum model. And we believe it's very important that we start adding into our curriculum to empower students to freely move between continuum models and lump parameter models. And normally they have been completely separate software packages and separate courses. And with the recent powerful development of Port Hamiltonian formulations, which allow you to have in the one mathematical framework both of those modeling approaches, we think is very important. And we're trying to adapt MICA to provide students with that experience. The virtual tutor is something that we're working on. It is going to take some while. We're pairing up with Weta, the New Zealand company that is famous because of its work on Lord of the Rings and Planet of the Apes and Avatar and a whole bunch of other movies. And so we're working to see if we can use that Hollywood-style realism achieved in those movies to bring that into MICA as a virtual tutor. I might add, our ultimate goal is in MICA is to eliminate the need for traditional exams or multi-choice tests, and to use the actual physical workstations where students are running experiments, but where the workstations can pose questions and effectively perform experiments on the students, so that the workstation itself starts building a model of the student's knowledge in a particular area. So we like to think that eventually the e-tutors are not only there to help tutor with the teaching and to resolve questions and so on, but also that e-tutor there is busily modeling the student's knowledge and trying to learn what their preferences are, so that if, for example, you're keen on music, then perhaps you teach periodic phenomena and resonance via music, whereas if you're into sports or something else, the method by which you're going to present material would be somewhat different. So this shows, this particular setup here is a MICA workstation to do fiber analysis. And in this case, it actually has a hair in the apparatus. And so you can do stress strain measurements on the hair. It's set up so that the electrical impedance transfer function of the hair can be measured. So as a function of strain, you can actually remeasure the electrical impedance transfer function, actually over a range from millihertz up to about 50 megahertz. And of course, you can deform the fiber. There's actually a tube that goes over the fiber and a setup which is able to humidify the fiber so that you can make mechanical and electrical measurements as a function of humidity. And you can see that it is 200 millimeters wide. And so the MICA workstations are largely built within a footprint of 200 millimeters by 200 millimeters by no more than 600 millimeters high. And you'll see shortly why that is important. But the idea was that if you have a room of 50 students, each of them with 50 different workstations, MICA workstations, their notebook computer together with the workstation would be no more than 600 millimeters wide, which is a little bit more than the width of your shoulders, so that you could pack a lot of students into a room, into a laboratory, if you like, where they were individually interacting with the MICA workstations. Of course, packing students in a room like that is not something that we're currently doing, of course. So this is actually a setup that I'm about to run an experiment on to show you the sequence. But basically, there's a mechanical beam here, which is actually a metal ruler. It's clamped at one end, actually magnetically. The free end has a little setup where a Lorentz force actuator can exert forces on the end here, and that allows you to drive that metal beam dynamically while the position and force is being measured. So it also has, under computer control, a copper eddy current damper, so that the amount of damping as seen by the beam is actually under computer control. So it can be varied so that you have a damping parameter of basically 0, in which case this beam is highly underdamped. And when you move the copper plate up towards the magnets, which form part of the Lorentz force actuator circuit, the damping goes down to about 0.05, so it's highly damped. So I'm now going to do a demo of this. And so if we can just, I'm just going to stop the share screen, and I'm going to move that to the Mathematica analysis environment, which is actually going to run the experiment. And then in the other screen, which is labeled MICA, you're actually going to see the actual setup. So maybe if we can just switch over to MICA, the MICA screen, so that we can see the experiment being run. And yeah.
Ian, I think you might need to stop sharing your screen for that to work.
All right, I'll do a stop share. Ah, there we go. Excellent. So, so this is the beam here that's got the Lorentz force actuator on the end of it, and we're now actually going to generate a stochastic binary signal that's going to be used to do a dynamic experiment on that beam, and then we're going to use linear system identification techniques to actually characterize the behavior of that system. So if we can now go back to the other screen, and we'll bring up the lecture notes. There we go. So this is what the student would see. And so there's a little bit of background that they would go through. And here, what we're doing is making, so this is, we're going to analyze these data, we're going to run the experiment and then analyze the data in real time. We're just setting up the A to Ds and D to As and the other, the micro-stepping motors and other entities that we need. We're just checking that we've got an offset that is roughly 5 volts, offset voltage. And now we're just going to do a quick measurement to get the baseline noise measurements of this system. And here they are right here. And so just so that this is truly in real time, I'm going to delete all the output here and rerun that, because I want to show you that we're actually gathering and analyzing the data in real time. Okay, so there's what we just collected, and that looks like bit noise, which is what it should be, because our noise levels are in the order of 1 micrometer. And so that's down, you know, in plus or minus a bit in terms of the position sensor. Now we're going to generate some Gaussian white noise. We've just done that. And we're going to low pass filter it. So here we're defining a second order Butterworth filter. And here, you know, we're just showing the gain part of the Bode plot of that filter. And now we pass the Gaussian white noise through that filter to produce Gaussian non-white noise. And here we're just doing that convolution. So in black there is now the Gaussian non-white noise. And we're now going to hard limit that to turn it into a binary signal. So in red there, you can see the hard limited binary stochastic. So that's binary non-white noise. And that is what we're going to pass as a current into the Lorentz force actuator to produce a non-white binary force applied to that beam. So this is the actual input that we're about to deliver. And now we're going to run the experiment. And so if we can just flip to the other screen, maybe I have to stop share again. If we can go to the MICA screen, perfect. And then I'm going to try and get back to screen and start the experiment. Okay, and now you can see it moving. And that's as a result of a stochastic binary current being applied to the Lorentz force actuator. And so it's not a large movement, but it's sufficient to characterize the dynamic behavior of this system. So if we can now go back to the other screen, and I will bring up the Mathematica notes again. Excellent. So now, having run the experiment, I would, if this was being done not one-on-one with a student, but in front of a class of students, and we don't like that. We don't like MICA being used for lecture room demos, but we do understand that sometimes they will be used for that. Here we're now just broadcasting the data we've just collected out to every student so that they can pull in the data set and analyze the data alongside the professor analyzing it. So here is our input, and right here is the measured output, the displacement of that beam. We can look, because we've time-stamped every sample, we can look at the jitter. And here you can see that the average time between samples was 2 milliseconds. And what we're going to do here is actually resample the signal with appropriate anti-aliasing filters to make it actually 500 hertz equispaced samples. And now we'll compute the probability density function of the input, and indeed it is binary. We can calculate the cross correlation of the input, and here it is right here. So that's the input autocorrelation function, I should say. And here's the output probability density function. We can compute, although we don't need it, it turns out we can compute the output autocorrelation function. Of course, the Fourier transform of that is the output power spectrum. Now we compute the input-output cross-correlation function. Here it is right here. And so now we use Toeplitz matrix formulation to deconvolve the input autocorrelation function from the input-output cross-correlation function to yield the, an estimate of the system impulse response function. And here it is right here. So you can see that this measured impulse response function, which is calculated not by putting an impulse in, but rather by putting a stochastic continuous input in, and then using linear system identification techniques to determine the impulse response function. Of course, the Fourier transform of this would be the frequency response function. And remember, we haven't modeled this as yet. This is just a non-parametric measurement. You can see that it's got some second order behavior, and there's an oscillation on top that may be evidence of even higher order behavior from this beam. And it turns out that that oscillation is in fact a higher order mode of oscillation of that beam that would show up if we did, for example, a mechanical dynamic finite element analysis of the beam. So here, what we've done here is we've convolved the impulse response function with the input to make a prediction of the output. And we've plotted the predicted output and the measured output, and they're almost identical. So for many students, this will be the first time that they realize the power of linear system identification techniques to make a prediction of the output of a system, even when it's perturbed by a wild input, such as we've used here, a stochastic binary input. And here we've computed the residuals, and you can see that the residuals are very low, indicating that we've made a pretty good prediction. We can compute the variance accounted for, the percentage of the variance of the output that is accounted for by the linear dynamic model. Remember, this model is non-parametric. We haven't said that it was first, second order, or whatever, but we've accounted for 99.8% of the variance. So this would be a clear indication that there would be no reason to go to a nonlinear dynamic analysis, because almost all of the behavior of this system is characterized by a non-parametric linear dynamic model. So now we go through and compute the frequency response function shown here, because remember, once we've got the non-parametric impulse response function, we can Fourier transform that to get the Bode plot, the frequency response, and here it is right here. So here you can see clearly some second order behavior, but there's something else appearing at about 47 hertz, and that turns out to be the second mode of resonance of that beam. So let's have a look at the phase part of the Bode plot. And so here, students, can learn that, well, you have to unwrap the phase, and so we introduce them to a phase unwrapping algorithm. And here we've now unwrapped the phase, and if we zoom in, we can see that certainly up to about 30 hertz it's behaving as a second order system, rolling off at about minus 180 degrees, but then at higher frequencies it becomes more complicated. But what we can do, so far everything we've done is with a non-parametric model. We can say, well, what about if we go parametric? How much do we predict if we just have a static model? Well, we've just done exactly that. We've fitted a static model between the input and the output, and we're only accounting for 2% of the output variance, which is pitiful. So then the simplest dynamic model would be a first order linear model, and we go ahead and fit that. And now, in order to fit that, students are introduced to using a nonlinear minimization technique. In this particular case, Levenberg-McQuart minimization. And here is now the prediction in blue together with the actual output, simply using a first order model. So a first order model clearly is not doing very well, but let's look at the residuals there, and the residuals are almost as big as the output variation itself. And indeed, if we compute the variance accounted for by that linear dynamic model, it's only 37%. So now we fit a second order model. And we already suspect that a second order model is going to represent some of the behavior of this system. And so here we're just using the power of a symbolic computer language to be able to go from the general form of a second order transfer function in the Laplace domain and inverse Laplace transform that to get a symbolic impulse response function, which we've just plotted. We'll go ahead and now fit that to the data. And this is actually not a fit as yet. That's just, trying some parameters. But here, what we're doing is allowing students to vary the gain manually, the natural frequency manually, and the damping parameter to try and fit by hand. And you can see the sum of squares fit shown on the other side. So it's always good to allow students to go ahead and manually fit a model. But now we go ahead and do that automatically using Levenberg-McQuart nonlinear minimization. And so here's the best fit second order model shown in blue, but we've clearly failed to capture this higher order behavior of this system. And so this is the prediction of the second order model. It does a pretty good job. And here's the residuals, not quite as low as our non-parametric model. We've accounted for 98% of the variance. And now we go ahead and fit a fourth order model to see if we can pick up the higher higher order behavior of this system. And, you know, I'm going through this way faster than you'd normally go with a student, of course. And there we fitted actually the fourth order model, and it's doing a remarkably good job in predicting the output, almost as good as the non-parametric model. And so here we would then just quickly compare a static model with a first order model, with a second order model, with a fourth order model, and with the non-parametric model, and plot the variance accounted for. Variance accounted for doesn't punish you for over-parameterizing the model, so we can use the MICA information criteria for that. And the MICA information criteria is showing us actually that the best model is the fourth order model with 6 parameters. We can go and compute parameter sensitivity functions to show what happens as you vary the parameters on each side of the optimum value. I'm not going to go through them all here. And of course, once we've got our fourth order model in parametric form, we can now symbolically Laplace transform that to get the transfer function. And it takes a little bit of time actually to compute, to do that symbolic Laplace transform. But here is now the best fit fourth order transfer function to those data. And here's the phase part. And now, of course, we can show the fitted fourth order model together with the actual measured frequency response function. So that's a quick example of the sort of analysis environment that we're providing with the MICA setups. So in the last few minutes of the presentation, I wanted to go through and let's see if I can bring this up. Okay, all right. So this is an example of a portable MICA setup where we actually had a second order low pass filter, actually a Salem key analog second order filter that the students were all sent because of COVID-19. And they actually performed system identification to try and determine the symbolic model for that particular system. So we also have thought about how we transport these models from these workstations from one student to another. And here actually is a MICA setup with about 10 different position sensors all running simultaneously. And that's a setup used to show the properties of different position sensors, but it's inside the MICA transportation case. What about if we truly have to run MICA remotely? We've put into the MICA setups the ability to be run over power over Ethernet. Of course, if we were just running them on their batteries, they would go flat, after a period of time. But by having a combination of batteries to provide brief high currents that we need, together with power over Ethernet, we're actually able to run these continuously without having to change batteries. And so that's something we're currently experimenting with. Here's an example of some of the MICA setups. If we can just go over to the MICA camera, I maybe have to stop screen share for that again. Okay, so you can see here some of the MICA setups, something to measure viscous drag and viscous unmixing, light source spectra, magnetic fields, gas laws, heat capacity, vibrations, springs, sound velocity measurements, temperature measurements, friction, Seebeck effect, and so this particular one here is the fiber analysis setup that I mentioned before. We're also building them for use in biology, so this is a bacterial growth setup. Here we have all the main methods of doing cooking being compared on the one setup. So, you know, induction heating based cooking and joule heating, and here we have tensile testing, a water analysis setup, catenary, so that if you're teaching you know, the mathematics of fitting a model to a measured phenomena, in this case a hanging chain, a catenary. We have ones again that are more suitable for perhaps use in teaching math. So this particular one here, we have a 240 frame per second camera looking at that, and if you pull out a frame when it's normal to the camera, and then go ahead and use image processing and fitting techniques, students can discover that that shape there is a parabola. And of course you can change the speed of this to create different parabolas. And here's another nice one, solar cell. So here we have an LED array that's capable of producing about 120,000 lux on the surface here. So that's more than the 100,000 lux of sunlight at noon, and actually have a thermal camera in here that's looking down on this solar panel to look at the thermal distribution. There's an array of Peltier effect coolers underneath here so that students can measure the efficiency of the solar panel as a function of its temperature. And as before, the students can vary the load as seen by the solar panel in order to optimize energy per unit time extraction from the solar panel. And once again, we have a micro-stepping motor, so that this can be manipulated remotely should the student not be in front of the setup. So, so I know that our time is up. We've got just another couple of minutes. Is that okay, Dan?
Yes.
Yeah. So I'm just going to go back to the other screen now. Okay, so with any luck, we can bring this screen up. Maybe have to do another, try the screen share again. All right, let's try this. All right, there, share it. Okay, I think we're back in business here. All right. So again, this is just more of the setups that we've just seen. Here's sort of a list of some of the ones that we've already developed and are under development. And For example, if we look across the different MICA setups, these are the fundamental constants that one or other of the MICA setups is in fact measuring. And we're about to add Newton's gravitational constant and, via a Cavendish experiment, and electron mass via a Bainbridge setup, as well as a Millikan oil drop MICA setup. So I'd like to end by just mentioning a few of the MICA sensors that are under development. So this here is something we've been developing for some time, which is a handheld mass spectrometer. So we wanted to have in MICA the ability to have some advanced instrumentation. So we have a mass spectrometer, a Raman spectrometer, actually a nuclear magnetic resonance spectrometer is the latest thing we've been working on to miniaturize. This is a MICA cloud chamber that we've developed, and this is just showing a video of the emissions as measured by that cloud chamber. We have, again, a nice fluorescence quench sensor using linear system identification techniques. A potentiostat and a galvanostat, more for use in material science and chemistry. We have a miniature gas chromatograph, actually a pretty high resolution gas chromatograph. And we're working with Professor Khalil, who I think is on this call, on a couple of different optical physics-based setups, including one involving Mach-Zehnder interferometer and the measurement of the output from a tungsten filament, as well as to measure the spectral output from the sun as measured outside on a sunny day. So that completes our presentation. So I think, Lynette, if you can join me and we'll take any questions. Yes.
I think there's one question that I think would be good to address before transitioning to Dr. Dia. One person asked about the number of connections that could be made within a MICA workstation and how you might manage large numbers of students in the classroom.
Yes, so that's something that we've put quite a bit of time in and haven't completely resolved as yet. So at the moment, with the power over Ethernet, so first of all, if each student has their own notebook computer, and that notebook computer is directly connected to a MICA workstation, you can have thousands. There is no limit. The limit becomes when now you want to set up a remote classroom, perhaps we'll say with 100 different MICA workstations. We've got 50 now, but eventually we might have 100. And now you want to be able to access each one of those. So any given power over Ethernet node, we're limited to 11 MICA workstations. But all we've got to do is just have a sort of hierarchy where you fan out. So you might have one Ethernet switch, we'll say, with 8 outputs, each going to another one with 8. Now you've got 64. If each of those is going to another 8, then you've got 512. So we solve that limited number of Ethernet connections just by branching out. Under Wi-Fi conditions, we're just as we speak, actually experimenting with a mesh network. So the total number of wireless setups that we can have is limited in a wireless network to about 8. So if you have a single computer and you now want to wirelessly connect that computer, we can connect that single computer to 8 MICA modules or 8 MICA workstations. We're just about to expand that dramatically by setting it up so we can form a mesh network. And under those conditions, we should be able to get about 256 different wireless entities being that we can communicate with.
Thanks for that answer. So if you don't mind, we do have some other questions, but I'd like to give Dr. Dia a chance now to present. And so welcome everyone. I'd like to introduce to you, many of you already know him, Professor Dia Khalil, who is Dean of the Faculty of Engineering at Ain Shams University.
Okay, thank you very much, Dan. And thank you, Professor Hunter and Professor Jones, for the excellent presentation. I enjoyed this presentation very well, although I am aware of the MICA process and maybe involved in many discussions with Professor Hunter before for the development of this MICA process. But for me, it's always a pleasure to hear it again and to follow up the developments done in the MICA process. I'm quite confident that it may make a transformation, a very positive transformation actually, to the way of teaching and learning worldwide. And I hope this will be done also in our Faculty of Engineering in Ain Shams University. I will make a very small presentations on developments we are doing to support actually the MICA implementations through our research activity in Ain Shams University. I don't know if I have the right to share the screen. Can I share my screen?
Robert, can you give Professor Dia that right?
I'll try and see if it will be. Okay.
There we go.
So can you see my screen now?
I can.
Yes.
So it should be. Okay. 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 So it's not 5 minutes, 10 minutes maximum to present our miniaturized FTIR spectrometers that should be integrated with the MICA platform. This was part of our research project for the MIT Center of Excellence, actually. So it has been based actually on the fact that we believe that the internet is now going everywhere, and the reach out of the internet all over the world is increasing with time. And it's not only all over the world, it's also in Egypt. The number of internet users in Egypt is more than 54% of the populations, and it's increasing with time. Maybe the quality of the service itself is not as high as we expect or as high as we want always, but the reach out is huge, and Egypt is actually one of the top 20 countries in which the internet, with respect to the number of internet users all over the world. And there is a transformation in the internet service now all over the world from just an internet of informations to an internet of interactions. And that's what we call the IoT, the Internet of Things, actually. And for this Internet of Things implementations, we need to have interaction through sensors and actuators mainly. And this is the main area in which I think the MICA process and the developments we are working on the micro levels can support very strongly. Because an internet sensor should be a very small size, weight, and low cost sensors also with respect to the benchtop sensors, should have low power consumptions, low level of maintenance, and so on. From these visions, and knowing that with the deployment of the Internet of Things, we need a lot of sensors and actuators all over the world, we have been working extensively in this area of building sensors and actuators that are compatible with these requirements for the Internet. And these sensors and actuators will be practically quite suitable with the MICA platform, actually. At the beginning, we focused on one of important, or we believe that's very important sensor, which is the spectral sensors. So we would like to replace a conventional spectrometer, benchtop spectrometers, by a spectral element, small element, using the MEMS technology. And why the MEMS technology? Because the MEMS is an extension of the integrated circuit technology, actually. I'm coming from the electronic domain, so we have been working extensively during the 30 past years in miniaturizing the electronic components on a chip. We have everything on a chip now, millions of transistors on a single chip and so on. And since about 30 years, we started also integrating mechanical components, optical components, thermal components, and so on. And this is the promise of the MEMS technologies, micro electromechanical system components. And then as an optician, I add the O also to be MOEMs or optical MEMS components. And this MEMS technology, as we expect, will be following the same track done by the IC technology. So it's expected to have very miniaturized components with small size, weight, and power consumptions, sub-micron precision up to some millimeters in dimensions. And it can integrate both optical, mechanical, electronic components. And the most important is that it allows the capability of batch processing and mass production. And this possibility allows to have some scalable solution, which means that if you produce this solution in a large scale, you will have very low cost for this solution. Exactly as what happened for the integrated circuit technology. In addition, if we add to this MEMS advantages, the optical advantages also in testing and characterizations, which makes the optical testing usually non-invasive, non-destructive, with few requirements of maintenance and replacement and so on. This makes the optical MEMS quite suitable for this era of Internet of Things or micro miniaturized components in the labs. So we have been working on what we call the deep rectified etching technology on SOI, which allows us to make some mechanical and optical components on chip. And with these components, we can build some optical system. This is an example of an optical system composed of beam splitters, fixed mirror and moving mirrors, and of course a light source to feed this system. And this how this system will look in practice. So it will be some by millimeters dimensions with an actuator. This will be the actuators, actually, the element that will make the mirror move. This is the beam splitters. And then you can have the input and the output either by fiber or free space coupling. And free space is actually preferred. And the idea of the actuator is quite simple. It's just a capacitors with a complex configurations to increase the area of interactions and reduce the distance, so you can increase the energy stored by these systems. And this is how it looks in practice. This is the comb, actually. So you have hundreds of fingers interleaved together, and you have some spring, and this spring allows to restore the mirror to the actual position. And this is a mirror, and this is a typical beam splitter things. All the optical systems will be in the rest of the components, actually. So by this technology, we can replace what we build on optical systems or an optical table into a simple chip, small chip. And then this will be part of a die of a complete wafers. So we can fabricate hundreds of these, 400, 500 of these optical systems. And with the aid of the electronics, we can make the controls, the data processing, the analysis, and all these requirements. This results in the first version of these spectrometers, actually, in which we have all the optical system on this chip connected by optical fiber and some electronic components for data processing, for the analysis, for the control, and so on. And this is how it looks like and how it's produced in mass productions, actually. Then we can use this element actually in building all the experiments, very simple experiments. It will be quite compatible with the MICA process. The dimension of these spectrometers is typically the dimension of a credit card, actually, with a thickness of about 1 centimeter for this first version. And this is an example of a simple experiment in which we can measure the butane lighter gas. So students can simply use the lighters to generate some butane gas, and he measures the gas and the decay of the gas with time. And this can be easily observed in the absorption line of the gas. So this is a typical absorption line get by the spectrometer. Actually, here is the spectrometer itself, and here's the light source outside just for the testing. So we imagine that the dimension here is something in the order of 10 centimeters and 10 centimeters, so it can be easily implemented on the platform of the MICA process. And here is the overall systems. It's 10 centimeters, 10 centimeters, 10 centimeters. And in this experiment, we have a standard gas cell with specific gases, and the student can, or the users can actually measure different gases, the absorption mix of the different gases, and identify the different gases. You can also do the measurements in free space to monitor the variation of the CO2 or the H2O vapor and so on. I'm focusing on the gas analysis because our project actually is on the building a gas analyzers. And this is an experimental setup in which we have a gas cell, huge gas cell, very small spectrometers here, and the light source on the other side. And the light is going inside the gas cell multiple times, goes to the output. And we can control the amount of gases and inside the cell, the different gases, through the different valves, classical valves, and so on. The experiment can be controlled by the laptop. In this experiment, it's connected to the laptop, and everything is controlled on the laptop, actually. However, we need to develop also all the controlling parameters, the pneumatic parameters here to control the gases going through the gas cell, in and out of the gas cell, to be compatible with the complete cell. But we have also building, we have the intention to build, actually, during our research project, an integrated gas cell with small dimension. This will allow also to have all a very small size. The second version of this spectrometer is done using some optical reflectors, optical molds, to have also compatible with small dimensions, and you have the light going in and out, and the detector is replaced by some dye detectors and so on. And then we have everything in a very small chip, which is few centimeters by few centimeters. This is the chip. Inside this chip, you have the optical head, the electronics also for the driver, for everything, and the optical core modules, which replaces the optical fiber for guiding the light in and out of the chip. And this is typically what we can do with this chip with a Raspberry Pi. We can connect this chip with a Raspberry Pi and use it to test different materials, for example, for food analysis, caffeine analysis, for polyester and plastic analysis, and so on. And everything will be connected to the computer to transfer the data and make the data analysis later on. And unfortunately, we have been shortened in time, so you are not able to send the small chip to Professor Hunter. It was programmed to have it in these demonstrations, but we didn't get enough time, it seems. So I hope it will arrive maybe next week or something like that. Due to the COVID-19, the transportation is still a little bit complicated. During also the presentation of Professor Hunter, I was thinking actually on the fact that I have observed two big phenomena that are quite interesting for me. First is that The system dynamic analysis is very close to what we are doing actually in electronic analysis. It's some signal processing and Laplace transformations or Fourier transformation. Then we get convolution and deconvolution. All these are the tools actually of the electronic domain. That's what we are using in our electronic domain for the circuit analysis, for electronic circuit analysis, and what we are teaching for the students. So it's very interesting to see that in the mechanical engineering side also, they are using the same language and the same tools all the same time. That's very good, very encouraging for me. On the other side, I hope I didn't take more time. On the other side, I have been thinking also in another option that could be very interesting, I think, and I will discuss it with Professor Hunter later on if he has time for that, is that with the MEMS technology, we can actually build a complete platform for which we have different mechanical system, mechanical components, mechanical diaphragms, cantilever, things like that. And we can measure the micro displacement easily through the capacitive sensing techniques we are using as spectrometers. And like that, we have a complete systems on the micro scale with a suitable optical system over these microsystems. The students can also study the micro phenomena easily, either on the microfluidic levels or the micromechanicals, because we have a lot of different phenomena that appear in the micro scales actually. The friction with the air layers in the combat drive actuators, some mechanical problems like that are very interesting to be studied and can be easily intentionally built on the micro scale with the MEMS actuators and used for the study later on by the students itself. We will be able to generate all the data from different positions and collect these data and make it very suitable for the students. For the
I love it. It sounds wonderful.
I'm sure of that. So let's work on it. I'll be quite happy to work on that with you, Professor Hunter, of course. With the blended spectrometers we have, which is nearly ready now for the experimentation, I think we can serve a lot in the basic and applied chemistry experiments. In addition to the gas sensing, we could use it for material science analysis, also for some, with the applied chemistry, maybe we need the students to have some deep machine learning also in addition to be able to make some chemometric analysis. I'm not sure that the students in our School of Engineering has studied the chemometric analysis or not, but I think it's something to be introduced also. It's important to introduce it in the chemical engineering study and certainly in the postgraduate study. So this is my comments. We are working in this project and we hope that we will be able to add some value to this fantastic platform, the MICA process. And I hope we'll be able also to implement it in our Faculty of Engineering. I'm now talking with the hat of the dean, acting dean of Faculty of Engineering. I'm quite interested to have this system built in our labs and used by our students on a large scale. And I will be working extensively in these directions by all the means I could have to have it implemented in our Faculty of Engineering. And I think Tamer will be also happy to support me in this. Professor Tamer will be also happy to support me in these directions. Yes, Tamer? Do you agree with me? I don't know if he's with us or no. Okay, thank you very much for listening, and thank you, Professor Hunter, for this wonderful presentation. If you have any questions, I will appreciate having your questions, of course.
That was wonderful.
So we have one more presenter today.
Yes.
Dr. Mohammed Ragab from Mansour University. Are you prepared to?
Can I make a quick comment before the presentation?
Yes, you may.
Yeah. So you know that your presentation was very enlightening, and I'm glad that you're seeing the thin lines between mechanical engineering and electrical engineering. If you recall, right in the center, I have been pushing very hard to make people think more broadly and outside the constraints of the department. Department lines are artificially drawn, and the knowledge base is much broader and much more universal than we think. And it is very important that we give this message to the students from the very beginning that there's much power in integrating the knowledge and using it beyond what we see as kind of short-term application and kind of classical and conventional way of thinking about it. So I think Ian and Lynette's presentation was very much on the mark in demonstrating that this is the reality of it, and by thinking a bit deeper into it, we can really not only help each other in the teaching tasks, but also help the students themselves grow to think more broadly and outside sort of the disciplinary constraint. So I will speak with Dr. Tamer, and for Ian and Lynette's benefit, Dr. Tamer is in the mechanical engineering side, and he is more on the educational side. I will speak for him. Hopefully, he will pick up the same theme that he will be definitely interested in seeing that kind of integration, at least at the level of using tools to demonstrate concepts and to develop approaches for designs and implementation. These tools and concepts should go beyond the department level. I think the department constraint is very artificial and should definitely be broken down at this point.
Yeah, I agree with you completely, Professor Onem, of course. Yes, the materials and tools that have been presented by Professor Hunter is actually part of the course of signal processing I was teaching for the students, actually, in the second year electrical engineering. So I've been teaching this course myself, so I enjoy it very well. And we are teaching the same phenomena actually on the laser science, even in the fourth years also, because it's a second order systems. So, you know, all the second order systems will have the same phenomena, the resonance phenomena, the damping phenomena, and the adjustment of the parameters are very close. And once you understand the idea itself behind such systems, you can apply what has been developed, at least for different systems. And this we usually used to do it actually in the science, transfer the developments, we call it some design reuse. So if there is some developments that has been done based on physical phenomena in a specific domain, we can reuse this design in a different domain with a minimal effort actually. And I'm working currently in the MEMS, and MEMS is a system by nature, it's micro electromechanical system. So I'm in touch a lot of time with the mechanical systems, and I didn't stop observing the similarity between what we see in mechanical systems and optical systems, mechanical systems and electronic systems. And this is why I'm quite interested in working with this. Maybe I will apply for a PhD in mechanical engineering if you accept it.
We will.
Maybe we can give each other honorary degrees. How is that?
It'd be a great honor for me.
I see a hand raised. I'd like to recognize Professor Adel.
Yes, good afternoon for everyone. And I have only a small comment on this discussion. Actually, we can say that any engineer have to have some common knowledge from the other departments. So we have mechanical engineering, electrical engineering, civil, and architect. But actually, nowadays, we have to integrate the information or the knowledge of any engineer or any student in any department to get some extra information and knowledge from the other. So this is already recognized, especially for the student at the final year for the BSc project. So I have some students make what we call thermal fatigue test setup. So they have to get some machine language, some another information from the electrical device, and so to complete this setup or this machine. So it is actually has a very good practice that we have mechatronics department and at our faculty. And this mechatronics department, some integrated between mechanical and electrical, and it is already under the umbrella of mechanical engineer department in our faculty. So I think we talk about we have to get some more knowledge and so on. Thank you.
All right, thanks for your comments. I think now will be a good time to transition to the partner in your university view from Mansoura.
Okay, yes, hello everyone. Can you hear me?
I hear you well.
Okay.
Yes.
Now I'll share my screen. Okay, can you see my screen?
I can see it fine, thank you.
Okay, thank you. Hello everyone, my name is Muhammad Ragab, Assistant Professor at Mechanical Power Engineering Department, Faculty of Engineering, Mansoura University. Today, I'll give a brief talk about experimental work in Mansoura University during COVID-19. I'll talk about 5 main streams or directions, which are recorded experiments, graduation projects, and mini projects, and virtual labs, and on-set experiments. I'll start by what we did before COVID-19. Actually, I'll start by recorded experiments. For recorded experiments, Mansoura University is one of the leading universities in Egypt preparing recorded experiments. Here we can see screenshots of physics experiments for fresh students since 2012. As you can see, 2012, and at our labs and uploaded to the internet to be accessible for all students. Other screenshots show uploaded lab experiments for second-year students of civil engineering. For civil engineering since 2012. All the recorded experiments are accessible for all students in the faculty. These are for recorded experiments. Now I'll talk about mini projects. Actually, in Mechanical Power Engineering Department, students by themselves started installing their mini projects at home before COVID-19. In mini projects, we divide the students into small groups, around 5 to 8 students for each group. And they can choose one idea which is related to the curriculum. And after discussion for their idea with the instructor, they start to manufacture and assemble the device. During this, they have to make videos for each step until they reach the final product. As you can see here, there are some examples for the mini projects students made by themselves at homes. As you can see, they start by the components, and then after that, they make short videos for the manufacturing process and final test or final step for the testing process or the test for the device. These videos actually act as tutorials for future students as peer-to-peer learning technology to teach them how to handle mini projects at home. Actually, we have some groups and collaboration between mechanical students and mechatronics students also to make some devices with remote controlling, but still all these devices are under development. As you can see here, this is a test of the device. And we have also here some mini projects, air preheater project, here some screenshots, and orifice flow meter, here the components and the final product and test. And here is another project to measure RPM motor. Actually, all these projects started before COVID-19, but now we
Dr. Ragab, I think there is a problem in the, I know that you have videos to show, and the screen is static. Many things that you have said, I know that you have materials for it, but your screen is still static on the first slide.
Not for me. I saw all the videos.
Yeah, I have seen also all the videos.
Yes, we see them clearly.
Maybe only for you, Dr. Nabil.
Please don't disturb Dr. Nabil. Let Ragab speak.
Okay, all these experiments and many projects were before COVID-19. Now I'll talk about what we did in Mansoura University after COVID-19. Okay, after COVID-19, we did also recorded experiments. After COVID-19 lockdown, the faculty started recording all the experiments, all the experimental work required from students during spring semester, and made it available on university website. As all students are not allowed to enter the university, they can follow up all their required experiments on the website. Here we can see some experiments. Here also workshops technology experiments about workshops technology. All these experiments are newly recorded, as you can see, April 2020. And also, how did we deal with graduation projects? For graduation projects in mechanical engineering department, majority of final year graduation students have to include experimental part in their graduation project. But due to COVID-19, some of the projects allowed to be theoretical or simulation. We have many students who use ANSYS Fluent or ANSYS CFX to do simulation to their projects, and some others only use simple calculations. But due to COVID-19, small or few students completed to do experimental work. And weekly sessions are held between students and their instructors to be up to date with their progress. The students who make experimental work do experimental work at homes because they don't allow to enter to the university labs, and they take all precautions and safety and health precautions against COVID-19. And what we will do in the next semester, we will talk about virtual labs. Actually, we started preparing for next semester based on hybrid learning because of the expected limited capacity. So one of the most important directions is making use of virtual labs technology. We started by making a list of open source virtual labs related to energy field. As you can see, this is around 20 virtual labs, and this is another 20. And there are some examples, as you can see here, example of making use of virtual lab technology. We started also making a list to prepare to buy some virtual labs to be available for Mansoura University. Faculty started collecting data from all departments to prepare database for the virtual labs to be accessible for all students. And now we will talk about on-set experiments. Next semester will be, as I mentioned before, next semester will be based on hybrid learning. So some decisions have been considered. Students' attendance will not exceed 50% of regular attendance before COVID-19. Students will be divided into small groups, and the new softwares will be bought by the university or by the faculty, and many other decisions. But now, in this case, students will be divided into limited groups and will be allowed to enter labs separately at different times, taking all necessary safety and health precautions. All labs will be sanitized each time and after the group enters the labs and before. Same precautions will be taken for graduation projects that will require the use of faculty facilities. That's how we dealt with COVID-19 and how will we do in the next semester. Thank you. Thank you for all of you, and for any questions, we are here. Thank you.
All right, thank you very much.
Thank you.
So it looks like you're really getting the students involved in helping to develop the curriculum and the associated equipment. There was a question posed in the chat earlier that I'd like to pose to all the presenters. And the essence of it is this. So we've brought in more sophisticated measurement and analysis. And now we have students grappling with topics like system identification. And there was a time when I think system ID might have been more common in a graduate level subject. And now maybe we're bringing it into the undergraduate curriculum. I don't know how early, maybe as early as second year. Is that a change that we think we're prepared to make, to take some of the advanced material, bring it earlier into the curriculum, and maybe ratchet up some of the expectations of our students? What do you guys think?
This is Ian here. I think that's a great question, Dan. And you know, when I went through, when I was a student, and we were learning Fourier transforms and actually coding them up at that time in Fortran, we had to learn about butterflies and all the other algorithmic minutiae associated with Fourier transform. And nowadays, of course, you know, you don't write your own Fourier transform routine as a student, or you don't normally do it, just in the same way as you wouldn't write your own Levenberg-Marquardt minimization technique or your own singular value decomposition algorithm. So I think there are some things that we can remove from the curriculum because you know, they've become sort of calibrated standards. I remember with singular value decomposition, there was actually for 10 years a major error in the algorithm that was being distributed worldwide. But nowadays, I think many of these algorithms have been honed and honed through time, and it isn't necessary for students to have to write them from scratch, or certainly not all students. That frees up time to, I think, bring some more advanced concepts that maybe in the past had been at the graduate level. And I actually think of system identification techniques as being the formalized scientific method. So they're no more the province of, you know, mechanical or electrical engineering than they are, you know, for physics or chemistry or even biology. But yeah, I think that's a time allocation problem. You know, how do we empower students with the sort of tools that they're going to need when they go out into the real world? And is it fair to have someone graduate with a bachelor's degree without at some point having done maybe some finite element analysis or some system identification?
Yeah, I think it's a good point. So we probably do have to take some things out, but the new tools will enable really new capacities. So I have a raised hand, Professor Ardell.
Yes, I have some experience about, that's because before COVID-19, I get the chance to travel to USA as a postdoctoral fellow and visiting professor at Department of Material Science and Engineering at Case Western Reserve University, Cleveland, Ohio. And most of the time I used to work on the fatigue test or fatigue properties of some new material. And one time I running the test and I have to change the condition of the test after a certain period of time. It was 2007 or 2008. The professor I working with, Professor John Lewandowski, gets the chance to get the program Team Viewer. And this Team Viewer program installed on my laptop. And when I was at home, I can connect to the MTS testing system or testing machine and stop the test, control the condition of the test, and then restart the test again. And I think this was very, very useful tools or program at this time. So we can use some similar program like this. And thank you.
Okay, thanks for your comment.
Dan, can I make a point? I think as we move forward, and this is something that I didn't talk about, but actually Professor Khalil did, which is the cost. You know, I think it's important that we make sure that any of these systems we're developing are not just to be used by rich universities, and but also for more, you know, less well-endowed universities than perhaps the ones that are on this call. And so this gets back to making sure that we develop these systems to be as low cost as possible without sacrificing dynamic range and resolution and bandwidth and so on. And this is where I think the point that Professor Khalil was making is that miniaturization, you know, absolutely can bring costs down. You know, if you look at the Michelson-based interferometers that Professor Khalil and his team have developed and very successfully actually commercialized, you know, they can be, you know, a $100,000 instrument. And he's brought it down, you know, by at least a factor of 100 times, and even more in terms of manufacturing cost. It's the same with our mass spectrometer. You know, our mass spectrometer is moderately high resolution, and normally you'd have to pay about $100,000 for one of those mass spectrometers. Our mass spectrometer, actually, the material cost is $100 in volume. So there's an example of bringing the price down by 1,000 times. So I think if we're careful in the way that we deploy and roll out these educational systems, we can make sure that they're also very low cost.
I saw a news report that they were trying to train dogs to be able to identify people positive for COVID-19 through smell.
Yeah.
So could a mass spec eventually allow for a very rapid COVID-19 test?
Potentially. And it's funny you should mention that, because we actually have a collaboration with another university where they have successfully used dogs to sniff out ovarian cancer from the volatiles above blood plasma. And they've done it successfully with mass spectrometers, dogs, and a carbon nanotube-based field effect transistor array technology. And all three of those are almost 100% accurate in double-blind studies. So yeah, there's, you know, the march of instrumentation moves on, and I think there are some very exciting potential low-cost developments that could even be used for, you know, detecting diseases as well as potentially COVID-19.
Yeah, I agree with you. Also a project targeting the identifications of COVID-19 using spectroscopy. It is just in the beginning, actually, get enough data, but it's based on the same analysis of non-invasive testing, non-invasive spectroscopic testing of the patients and identification of the existence of some virus. And I think there has been some work done for that for virus C and virus P before using spectroscopic analysis also. This what encouraged us to go in this project for the identification of COVID-19 also. But we are just at the beginning, so I don't know if we will be successful or not in this. I know in the PCR technique, they use some amplifications of the virus to be able to detect it. And this amplification requires some temperature recycling and so on to increase the number of virus per cells, which is simply a sample treatment, thermal sample treatment. And this what makes the cost a little bit expensive. If you can do the measurements directly, either by FTIR or by Raman spectroscopy, and be able to identify directly the COVID-19, I think it will be a great success. It will be very helpful.
So I see a follow-up question in the chat. You know, we had talked about the idea of system identification perhaps becoming more essential and more accessible. Are we proposing to bring it into the undergraduate curriculum? And I guess if so, where? You know, do you teach it in a course on differential equations? Do you teach it in the measurement and instrumentation course? Do you teach a little bit of it in many different classes? Where do you think it should end up?
So I feel very strongly that if you look at how engineering is taught, both in mechanical and electrical and chemical and so on, across different universities, students normally either are exposed to systems and signals, which includes control theory and perhaps sinusoidal-based system identification at the undergrad level, or they get exposed to continuum modeling and perhaps the finite element method at the undergrad level. But then they go out in industry, and you need both, because many problems, you know, require a continuum representation. But when you have to control something, normally it has to be a lump parameter, you know, simplification. So I think we're doing our students a disservice by just allowing them to do one or other of these major areas of applied math. And I think we've got to work really hard to integrating both of these two separate streams that you see going through both electrical and mechanical engineering and other areas of engineering. And actually one of our objectives in MICA is to have MICA setups where students are challenged and they can only solve a problem by using a combination of, you know, a finite element analysis and system identification, you know, around some lumped element within that continuum, to really motivate the need for both of those applied math areas. And as I said before, the beauty is that in the last couple of years, with Port Hamiltonian advances in Port Hamiltonian theory, you now have on the one mathematical framework the ability to handle both lump parameter systems as well as continuum systems.
Dan, can I make a point?
Yes, please.
Yeah, so I wanted to follow up by just saying that system ID is extremely important and definitely introduction to system identification from the mathematics and control theory side is very valuable, but also you can think of it, and it's a good way of motivating the concept of data-driven models. And data-driven models are gaining enormous popularity now with the expansion of AI. And if you think about AI as a way of training these very complex neural networks to learn by collecting data and sorting them out and figuring out how to do prediction based on these, system ID is kind of the beginning of that. So you're introducing a concept relatively simple compared to AI and all, but as a way to set the stage for students to think about not just physically based model, but also data-driven models, and think about how to expand on the concept of the data-driven models to go all the way to much more complex concept like AI. So, finding a way of putting it into the curriculum is, I think, is very important.
Okay, I'm scanning for raised hands. And looking at the chat. Okay, so Prophet L, I'd like to recognize you.
Yes, actually, I should say to Dr. Ragab, Muhammad Ragab, that Mansoura University was a leading university in the subject of recording the experiment and so on. And he mentioned that whole the department going to this idea. Actually, this may be occurred or happened at many other university, but on the scale of personal or individual professor. So I have myself actually I have to make a video recorder for the heat treatment experiment and so on for the student of sophomore mechanical engineering, and I have about 370 students, and so I can't. They cannot go to the heat treatment lab and make the experiment. I don't know how many, because we have a situation that to heat the sample, the oven usually take about from 6 to 8 hours to reach the required temperature. So we cannot wait until to start the oven at the early morning and then make the test. So we have to make a video record for the experiment and show the student in the lab, the video for the experiment. And that was, I know that it is individual character, but this happened in case or other and at different universities. But actually, at Mansoura University, they are leading in this way. I thank him very much for his presentation. Actually, I forget to say that.
Thank you so much, Professor Adil. As you mentioned, some professors take it as individual, but in Mansoura, the faculty itself started to do this. They started to prepare and put on the website of the faculty. So that was the different thing. And also many projects and the students who work at home by themselves also was good step for students to do experimental work by themselves. If we combine, as Professor Muhi said, if we combine work from home or work at home and virtual labs, I think it will be a great step even after COVID-19. Thank you.
Thank you very much. Thank you.
Yeah, thank you. So I would love to continue the discussion because I'm enjoying it so much, but actually, we have a meeting starting at noon of the academic regulations team to discuss our adaptations to COVID, which happens to be the subject of next week's seminar or workshop. So let me remind you that next week, that is Wednesday, 15th of July, we'll have our next installment of the COVID disruption sessions, again, starting at 10 a.m. Eastern Time or 4 p.m. in Cairo. So thank you for remembering about that adjustment to our plans. And I want to thank the speakers, Ian Hunter, Lynette Jones, Dia Khalil, and Mohammed Ragheb. Very much appreciate your thoughtful contributions.
Thank you.